afternoon, everyone, and welcome to our webinar, Metis Flood Modeling Case Study. So today it's going to be myself, Ludmila, and Michael Arthur from Metis Consultancy. Michael is a principal engineer, and he will share with us a case study on Ealing Borough in London. Our agenda for today is introduction, why flood modeling is important, and a case study by Michael from Metis Consultants. Main purpose of modeling. Why do we need to do a modeling? Why modeling is required? Mainly to understand existing processes, why and how the water flows, what happens with the water, to replicate natural water behavior, to actually map it and be able to see how water moves and where it goes, and to understand consequences of a change. What if which properties are affected? What if we add an additional development? What if there is an underpass? What if we create a flood wall, etc. If we go back to Oxford Dictionary, model, a simplified description, especially a mathematical one, of a system or process to assist calculations and prediction. So no matter how good we are and how great data we have, the model is still a simplified description of a real life. So we should never forget it, and we should always understand that model it can only go as close to real life as it can. It can never actually model the real life. So a good flood model, it requires understanding of hydrological processes. It requires quality data, such as rainfall, DTM, and infrastructure. If your surface data is wrong, your flood model will be wrong. If your rainfall is wrong, your flood model will be wrong. If you don't account the infrastructure which is in the area of interest, again, your flood model will be wrong. We need to create as accurate model as possible. The less assumptions we make, the better the results are going to be. And it's very important to do validation and calibration of our model. I believe Michael will cover a bit of it, how they validated their data and what they did in Ealing. Flood model outputs, they allow us to communicate predicted outcomes with stakeholders. In short term, it gives us ability to manage our catchment or site immediate needs, such as funding, for example. In long term, it gives us ability to better plan and manage for future. So if we have already area at risk, do we put more houses in there or do we not? And so on. Good model provides a long-term sustainable solution. So today, I'm going to hand you over to Michael, and Michael will introduce you to the Ealing area, which is a borough of London, and here I have a picture of London with a little point where Ealing is. And the company Michael works for is called Metis Consultants, and they were commissioned a flood modeling study to assess risk to local residents and businesses and advise on mitigation actions. So Michael Arthur will outline the background of the project, their modeling approach, using xpstorm, and the key outcomes of the work. At this point, I'm going to put myself on hold and mute and put Michael in charge.
So good afternoon, everybody. Hopefully you can see the first of my slides up on the screen now. Thank you for the introduction, Ludmila, and thank you for the opportunity to present to everybody today. Hopefully you find it interesting and useful. So as Ludmila's already outlined, I'm going to talk about a case study of two catchments we have been involved with within the London Borough of Ealing. So what I'm going to run through is a background to myself and Metis, and then run through the study locations and the modelling approach that we used, along with the outcomes and why they're useful. And then if there's time at the end, we can cover some questions. Please do enter the questions into the question box at the side of your little dashboard you should have up on your desktop. If we don't get a chance to answer them in this session, we will respond to them afterwards. So please do ask them, and we will respond. So a little bit about myself. My name is Michael Arthur. I'm a principal engineer with Metis Consultants. I've been working in the UK for about 8 years now, and prior to that, I was a senior engineer in New Zealand. Metis Consultants are a small niche consultancy, which is probably why you've never heard of us before. We are civil and environmental engineers, and we specialise in supporting local authorities with flood risk management and highway asset management. So we're London-based, but we work throughout England. And a bit of background about the study location. We worked for the London Borough of Ealing, which is a borough in the western part of London. It's a unitary authority and also a lead local flood authority. The history of flooding within the borough is generally limited, so as part of this work we assisted Ealing with running a borough-wide resident survey, from which we received about 650 responses, and the water company, the local water company here is Thames Water, also had quite a few sort of local drainage incident records, so we were fairly sure we were looking in the right place. The study was also supported by a surface water management plan that was done in 2011. The surface water management plan covered the entire borough, and one of the outputs from that study was the delineation of critical drainage areas. I think from memory there were about 10 critical drainage areas throughout the borough, and this case study covers 2 of those. So the first critical drainage area we're going to talk about is the Perivale one. It's a sort of mixed-use catchment, a really interesting mix of residential, commercial, industrial, and green space. So if I use, hopefully you can see the laser pointer when I bring it up. So a very big sort of industrial commercial area in the middle, and then residential areas to the north and to the south and the west. The sort of main sort of features of the catchment. It's a mixture of ordinary watercourses and main rivers. So the River Brent runs along the southern boundary, and there's a small ordinary watercourse that runs through the middle of the catchment here, amongst the Ealing recreation ground. There's a large bit of road infrastructure that runs through the middle of it, the A40, which is a major access route in and out of London on the west side. And the ordinary watercourse has actually been diverted underneath it through the use of a siphon and a pump station. So that obviously exhibits some quite significant residual risk for the local authority, in that the flooding to the north of the A40 is actually controlled by a pump station that's not in fact owned by them. It's owned and run by Transport for London. The catchment is a separated sewer network, so there's no combined systems in here. And the other main feature is the central line, one of the London tube lines running sort of through the middle of the catchment up here on an embankment. So a reasonably significant man-made modification to the topography as well. There was a reasonable history of flooding within the CDA. There were some known issues along this western side of the recreation ground, and the resident survey also highlighted numerous other issues throughout the catchment. The other critical drainage area I'm going to talk about is Northfields. Again, a mixed use of residential, commercial, and green space, of reasonably high interest to Ealing, because their civic centre is located in the north part of the catchment, so obviously quite interested in what goes on there. Similar set of main features, but a little bit removed from the main watercourse in this case. So the River Brent runs a little bit further to the south of this one, but still has some impact. And there's a small stretch of ordinary watercourse right in the middle of the catchment down here, which you can't actually see because of the scale. Similar to Perivale, there's a tube line that runs through the southern part of it, the Piccadilly line, on a combination of embankments and a cutting, so that obviously influences the overall flow paths. Again, similar to Perivale, a fully separated sewer network, and the catchment is possibly the watercourse of a historic watercourse potentially called the Radbourne. And we know this because there are several roads at the bottom part of the catchment that refer to this as a potential name. There were several historic flood incidences in the catchment, mainly centred around the bottom end of Lammas Park here, which also were verified by the Thames Water records of the area having similar problems. And the resident survey, similar to Perivale, showed numerous historic incidents sort of throughout the catchment. So the modelling approach we used was using xpstorm to build an integrated urban drainage model. I just want to recover the bits that Ludmila touched on earlier. So why modelling was important in this context is that we wanted to understand the flood mechanisms, and in Perivale and Northfield this turned out to be quite an important aspect of the studies, and then be able to use the model as a tool to predict the impacts of climate change and assess the performance of mitigation options that we would develop or will develop for each of the catchments. In possibly reiterating Ludmila's introduction, the thing I like to remember in any sort of training session I run on modelling, I always highlight that this quote from George Box: "All models are wrong, but some are useful." Unless you're spending a huge amount of money on your model, it's never going to represent reality in its entirety. So it's always useful to keep in mind that these are useful tools, but they're not the be-all and end-all of understanding what's going on. So you've always got to take a bit of reality and a bit of practicality in with what the model predictions tell you. So I'm going to run through the sort of key components of each of the models. Both were built using a similar methodology. I'll focus mainly on the 1D and 2D components because I think that the boundary conditions are less interesting and less useful in this context. So the 1D components of the model mainly consist of the pipes and watercourses. So for those unfamiliar with this modelling terminology, 1D stands for one-dimensional, which means that water generally only flows in one direction. It's a fairly simple representation of a watercourse or a pipe, and that's all it needs to be in the way that the flow behaves hydraulically. So we obtained most of this information from Thames Water. Thames Water had a reasonably good record of the location of the sewers within the network, but a fairly questionable quality of the information within that network. So there was a fair amount of work we did to interpolate invert levels and pipe sizes and things like that. And we also commissioned a survey to fill in gaps where critical information was missing. As I sort of mentioned in the introduction, both of the critical drainage areas have critical infrastructure within them, in particular the Perivale one with the Transport for London pump station and siphon. So it's obviously quite important to get detailed information around that. Then the watercourses were modelled using a combination of site observations, detailed topographic survey that we commissioned, and Environment Agency data from the main rivers. So you can see the images I've used here are just examples of how the model used this information. So the top image there is just a representation of the modelled sewer network, and then this image here just shows one of the cross sections that was used to represent one of the watercourses. Then the 2D or two-dimensional component of the model, again, the terminology, two-dimensional means that water can move in two directions within this model component. So it's ideal for representing the above ground impacts on surface water flooding. So a couple of examples of how we attacked this with these models: we used freely available LiDAR information to represent the topography. So the top image here shows a representation of Perivale, and you can quite clearly see the rail embankments and the cutting where the A40 goes through the middle of the catchment, and then the River Brent running along the south side there. So you can see that the LiDAR is a pretty good, accurate representation of the topography. And one thing to highlight is we use sort of a bare earth version of the LiDAR, which has all of the buildings and structures sort of stripped out of it. And the reason we do this is that we only want to represent the key parts of the urban environment within our model. Again, we want to balance complexity with model runtime and the effort required to build it. So we start with something relatively simple like this LiDAR representation, and then add back in the features that are important to us in the urban environment that we think are going to influence the above ground flooding most significantly. So the data set we use to add back in those features is the Ordnance Survey Master Map data set. Again, the right hand image here shows an example of what that looks like. So we use that to pull back in the key features that influence flooding. And in this case, the main ones were roads, buildings, and footpaths within the urban environment. So just a couple of examples of what the model actually looks like. So the left-hand image here is is what the model sees, in fact, if you like. So there's an example of a one-dimensional watercourse here with some of the pipes and the other things attached to it. And then you can see the slightly more colourful background is the LiDAR information. You can see the footpaths and the buildings also represented there. Then the right-hand image is an example of how you can use a combination of 1D and 2D modelling techniques. This one shows the Perivale model in particular, where the northern part of the model boundary was defined by the Grand Union Canal. Obviously, water isn't going to be able to cross that in any significant volume, but we did have to represent the pipes that went underneath it and the catchments that emptied into those. So we chose to do that in a more simplified approach because we weren't interested in the above-ground flooding of those catchments. A couple of examples of how the 2D model works. So you can see on the left-hand side here is the Ordnance Survey Street View data set, just showing what the topography and the local environment looks like. And then on the right-hand side is what the model sees essentially. So you can see how it picks out all the individual buildings, it picks out footpaths, all the ancillary buildings around the main ones, and this is, if you like, this is the model's view of the world, and it divides all this up into little boxes and uses that in the 2D computation. Just to highlight the statement before about all models being wrong but some being useful, this allows us to see what the model sees and make sure that we're looking at the key components of that urban environment and how they might influence overland flow. So why is this useful? It helps us understand the mechanisms of flooding and what residual risk might exist in the catchment. I'll talk a little bit more about why this was important, especially for Perivale, within my future slides. Helps us count the number of properties at risk, what kind of properties they are, what risk they are, what probability they might be flooded to, and the severity of that flooding. And this all feeds into the standard flood and coastal risk management funding applications that all lead local flood authorities can use to access funding for capital projects to manage flood risk. It also helps us assess what the future impacts of climate change might be. This particular diagram shows the 1 in 100 year event plus climate change, so it's a fairly extreme example of what the flooding might look like. Also helps us assess the impacts of development. So, for example, if you were changing the land uses up here, it might in the industrial area converting that to a residential area potentially, it would help us assess what the impact that might have on the lower parts of the catchment. But it also helps us assess how the potential sort of flood mitigation options might behave in the real world. So a couple of other examples of why this is useful. So you can see there's quite a good level of detail here that the model gives us. So you can see this is a velocity vector map, so it basically shows a little arrow indicating which direction the flow is going into, and the length of the arrow shows how fast it's going. So you can see here it provides a very quite good representation of the urban environment. You can see the water flowing down the road, and then in between the buildings, and then spreading out again on the lower side of the building. And then you can also see the impact of the road. In that the flows, as they would in reality, preferentially run down the centre of the road, and the roads have a fairly significant impact on the overall flood mechanism. So moving on to why this is useful for the two case study locations. As you can see from this diagram, that there's quite a few properties at risk potentially, but the depth of predicted flooding is generally low. So the extent looks quite severe, but the actual number of properties at risk is actually relatively low. It highlighted that the underpass here and the siphon and pump station that serve it is at a reasonably significant risk. And it also highlighted that because of this distributed nature of the flooding, that there were quite a lot of opportunities within the catchment for highways-based subsystems and green space for mitigation. So these are relatively low density residential areas with plenty of space around the roads for rain gardens and permeable paving and that kind of thing. But I guess the major outcome for Ealing was understanding the risk to this underpass, and it highlighted the fact that they didn't actually have much control over it because it wasn't their pump station, it wasn't their siphon that controlled that risk. So if this pump station were to fail, then obviously a lot of the flood water would remain on the north side of the A40 here, which is a reasonably significant residual risk for them. Then for Northfields, The flood risk was generally well validated by the incident information, especially down the southern part of Lamos Park here. There's a fairly significant number of properties potentially at risk, and the mechanism through which they were flooding was mainly influenced by man-made changes to the catchment. So you can see the Piccadilly line, rail line running through the middle here. It's up on an embankment in the middle. You can see that provides quite a significant overland flow obstruction to the catchment. It also highlighted that the flood mechanism was very different to what we expected it to be, and that there was already a very large sewer diversion in place that Thames Water had built historically that diverted quite a lot of the catchment flow away from the natural flow paths down this way and to the west side, and adding it to the Brent further to the west. So what we thought was the historic flow path of the Radbourne probably is the historic flow path of the Radbourne, but has been heavily modified by a very large sewer system. Good to know for the council, because all of the asset information is from Thames Water, and Thames Water obviously managing this big diversion, so it's good for them to know the diversion exists. It also gave a good partnership basis for delivering a solution, because there were some shared issues around the southern end of Lamos Park here that the Thames Water also wanted to address. So there's a really good opportunity here for partnership working between Ealing and Thames Water to deliver a mutually beneficial scheme. So why is this useful for local authorities? There's lots of reasons, but I'm going to just run through the bolded and italic ones on these slides. So for local authorities, in particular, it allows them to target highway maintenance and watercourse maintenance. So a good example of this was Perivale, where the wide extent of shallowish flooding you could quite easily manage through targeted maintenance of gullies, improving the assets around those areas, and knowing that key watercourses have quite a big influence on local flood risk. So it means they can take a risk-based approach to sort of allocating that maintenance budget in the right places and the right frequencies. Again, Perivale is a good example of the second point I want to make for local authorities, is that it's good for emergency planning and incident management. So they're now obviously well aware that the pump station in Seifert and Perivale is of quite significant importance to them, and if it does fail, they need to be aware of it and manage the risk associated with that. So it gives them a good basis to go and talk with the asset owner and develop a contingency plan for that. For private developers, this type of modelling helps them contest EA flood zones or local flood mapping. Often the local flood mapping that's been done is very high level and can be of low accuracy in some areas. So this kind of detailed study helps develop a much more detailed understanding of what's going on and practically manage risk within sites, and you can sort of open up larger parts of development sites by demonstrating the risk is different from what the national mapping says or can be managed more effectively. And that sort of leads me on to my second point for private developers, is that you can use these types of tools to really clearly demonstrate that the proposed mitigation you have in mind will be effective and can be effective for the development that you're proposing. So I think that's all I've got I've got time for today. I think there's 5 minutes or so for questions if Ludmila's collated any useful ones. Ludmila, do you want to? I'm happy to answer any short ones, because we've only got 5 minutes, but otherwise I'll answer the rest of them after the session.
Thank you, Michael. We have one question which asks, how long did the modelling take?
The modelling itself is a relatively quick task. The integrated model can be built, if you've got sort of one person sitting on a modelling machine, you can build it in about a month, maybe 2 months, depending on the complexity and the size. The thing that takes a while is collection of the background information and identifying where you need survey and collecting that survey information. So these models took about, I think it was about 4 or 5 months to develop, because there were sort of various sort of start and stop points where we were waiting for information and going out and surveying things and things like that.
We have a few more questions, actually. As you mentioned questions, people started typing them in. So there is a question from Mark. Please, can you let me know what runoff rainfall methods were adopted in the model?
These use a combination approach. So what we do is we take all of the buildings and roads and treat them as 1D catchments and use a very simple rainfall runoff method to route that flow into the model, mainly into the pipes. And then we use a direct rainfall approach of the 2D component, which is literally just tipping water onto the 2D surface and having some land uses defined as to how that water might behave. So there's various tools you can use there to define what the flow resistance and the infiltration and the initial abstraction is for all the types of surfaces that we've put into the model. So lots of people possibly use the sort of flood studies report or the FEH methods for this kind of thing. But for an integrated model, especially in an urban area, I think using this kind of approach is much more representative of what actually happens in an urban environment.
Michael, now I have a few more questions for you. In terms of surveys, how do you decide full scope of works from aerial survey or topo? Or basically, how did you define the boundaries of your work, or were you given them?
So in terms of the catchment area is defined based on the hydrological catchments. So we looked at the topography and the drainage network to define the sort of the critical drainage area boundary, if you like. Then the survey work, we used freely available information as much as we could, such as LiDAR and ordnance survey mapping, which is freely available to local authorities, to define the majority of the above ground model, if you like. Then the below ground model, so the pipes and the other bits and pieces, we used Thames water information as much as we could, and then once we'd reviewed the Thames water information, we then used that to sort of develop a prioritised manhole survey to go and look at the manholes that we thought were the most important to understand their impact on the model. And we also picked up cross-section information along the key watercourses. And I think a good point to make here is doing that survey on, once you've got down to the site-specific survey, it's important to target that in the areas of highest risk. Lots of people will start this sort of model build process and want to go and survey everything just because they want perfect data for the entire model. And I think an actual better and more cost-effective approach is to sort of build the model sort of 90% of the way there first, figure out where the critical bits are, and then go and survey those rather than spending money going on surveying everything when you've got everybody's working off limited budgets and need to show efficiencies and cost savings in this kind of work.
Thank you. I think your answer covers a few more questions where people were asking how did you verify the LiDAR data and accuracy. So you just did say that you tried to use as much as you could the Thames water data and the manhole levels. What return periods have you used, and what was the % of climate change you applied?
We used quite a wide range of return periods. The key ones are matched to the flood and coastal risk management grant and aid process. So in terms of Ealing gaining more funding to carry this work on and potentially fund capital works for mitigation, we need to demonstrate what's known as outcome measure 2 within the DEFRA policy for this. And so that's basically around moving residential properties from one risk banding to another. So the risk bandings are very significant and moderate. Very significant being, I think, around a 1 in 20-year return period event, very significant being around 1 in 40, and then moderate being about 1 in 100. So those were the key events we ran. Then we also looked at the 1 in 30, the 1 in 200, and we'll look at the 1 in 100 plus climate change. Then the climate change allowance we used is, I think it's 70%, which is the most conservative value currently published by the Environment Agency for flood risk assessments.
One more question, if you used any real-life gauges to verify the flows? No, the timescale of the study didn't allow us to install gauges and capture meaningful events. For calibration of essentially what's an integrated sewer model, it's very difficult to capture useful events with a short-term flow survey. Even if you're purely modelling the sewer network by itself, in a 6-month period or a 1-year period, you'd be very lucky to get a very significant event. And given we're most interested in very significant events, it's not generally worth the effort to put in gauging for the very low probability you're going to capture one of those events during the gauge period. Thank you, Michael. There are a few more questions on mitigation, but I believe perhaps we'll have a follow-up webinar when the model will be finished and the work will be done on all the mitigations. So you can share maybe 1 year from now what actually have been done with the site and how it all progressed. Thank you, Michael, for joining us today. The case study of 2 drainage areas in Ealing Borough. I'm going to conclude for now. So benefits of modeling, they are very clear, but just to refresh, we gain detailed understanding of flood mechanisms and residual risk. We identify properties at risk, number, time, probability, and severity. We provide evidence for funding. We understand the impact of climate change. We assess impact of new developments and identify optimum mitigation measures. If any of you will have more questions for Michael, and if you haven't noted his email address, you can just direct it back to us and we will put you in touch with Michael so you can directly discuss and share experiences. At this point, I'm going to move on into upcoming events. We are having a Bristol workshop next week. So if you haven't registered yet and you are in Bristol area, please register. It's free of charge event, half a day long, mainly covering microdrainage legislation and flood risk assessments. We do have microdrainage training in Newbury, A, B, C, and D courses, end of May. We do have Newcastle workshop beginning of June. So if you are in Newcastle area, please register, feel free, there are still spaces. We have a microdrainage training in Glasgow, which is, I think it's been a while since we run a training in Scotland. So if you're in Scotland and you want to attend courses A or B, please come on our website or give us a call, drop us an email, and we will instruct you how to proceed with booking Glasgow training. And we have in July Manchester training, again A and B. So please, again, contact us if you wish to attend this. At this point, I will say goodbye and thank you, Michael, again. Thank you so much for joining in and have a good day.